Okay, good morning, good afternoon, and good night to everybody. Today we'll discuss about the surface tension. This is the fifth lecture on physics one, and in this chapter we'll discuss about the what is surface tension, and what actually we will also discuss about the molecular effects on the surface. So different kinds of molecular uh, force, then adhesive attraction and cohesive. So surface tension and surface energy, capillary rise or fall of liquids, determination of surface tension of water, mercury and soap solution, effect of temperature, some real life examples. And the previous lecture was lecture 4, and that was about elasticity. First of all, what is fluid? Actually, a fluid is a substance which deforms continuously or flows when subjected to shearing force. Okay. In fact, if a shear stress means actually pidon is acting on a pressure or is acting on a fluid, it will flow. And if a fluid is at rest, there is no shear stress acting on it. So uh, fluid flow equals to shear stress, and yes, fluid rest, shear stress, no. So there are two types of fluid. Actually, shear stress in moving fluid, if fluid is in motion, shear stress are developed if the particles of the fluid move relative to each other. Adjacent particles have different velocities cause shape of the fluid. And on the other hand, the velocity of the fluid is the same at every point, no shear stress will produced, and fluid particles are at rest. So this is the snapshot for different fluids. And difference between liquid and gaseous, this is the basic difference between this liquid and gaseous. Difficult to compress and often regarded as incompressible. Easily to compress and change of volume is large, cannot normally be neglected and are related to temperature. And liquid occupies a fixed volume and will take the shape of the container, but in gas, no fixed volume. It changes volume to expand to fill the containing vessels. A free surface is formed if the volume of container is greater than the liquid and completely fill the vessels so that no free surface is formed. There are actually two types of fluid, Newtonian and non-Newtonian fluids. Fluids that obey Newton's law refer Newtonian fluids or of viscosity. And this is the Newton's law of viscosity is given by the formula, this one. And this is the example: air, water, oil, gasoline, alcohol, kerosene, benzene, glycerin, etc. And tau equals to mu equals to ddx dy of u, where tau is the shearing stress and mu is the viscosity of fluid, and the rate du divided by dy equals to shear rate of strain or velocity gradient. So the function mu is the function only of the condition of the fluid, particularly its temperature, and magnitude of fluid velocity gradient has no effect of the magnitudes. So Newtonian and non-Newtonian fluid that do not obey the Newton's law, and it is called non-Newtonian fluids. And the velocity of the non-Newtonian fluid is dependent on the velocity gradient as well as known as the condition of the fluid. So this is the characteristic of Newtonian fluids and the non-Newtonian fluids. So rate of shearing for Newtonian and non-Newtonian fluids, there are, and the units primarily we have to use these types of units for measuring: length, meter, mass, time, temperature, current, luminous intensity. The unit is candela. And this is the derived units we have to use in different problem solvings. And surface tension, we are talking about the, actually this in Bengali, Pristotan, and this is the Newton per meter. So unit cancellation procedure, And now, intermolecular force. What is the intermolecular force? So the force of attraction or repulsion acting between the molecules are known as molecular force. The nature of thermomolecular intermolecular force is electromagnetic. So there are two types of intermolecular forces. One is cohesive force and another is adhesive force. So the force of attraction between molecules of same substance is called force of cohesive. This force is lesser in liquids and least in gases. The force of attraction between the molecules of the different substance is called the force of adhesive. But in adhesive, there are different substance, and but in cohesive, the same substance. This is the difference. So, for example, two drops of liquid coal sink into the one when brought in mutual contact. It is difficult to separate two sticky plates of glass welded with water. It is difficult to break a drop of mercury into small droplets because the larger cohesive force between the mercury molecules. Similarly, for example, adhesive force enables us to write on the blackboard with a chalk or with a pen or with pencil. A piece of paper sticks another due to the large force of adhesive between the paper and gum molecules. And water weights the glass and glass surface due to the force of adhesive. So these two types of force makes actually intermolecular force. And now we'll try to understand what is the surface tension. Uh, so now, what is the actually surface tension? This is the actually practical view for us. This is the mosquito. What happenings here? Bug is walking on water. Why is this possible? So it doesn't weigh much. It's spreading its weight out. The downward force are less than the effects of a surface tension. This is actually real life example for us. Now, a molecules in the interior of a liquid is under attraction force in all direction. This is the actually, and that means the force is distributing in the direction. However, the molecule at the surface of a liquid is acted on by a net inward cohesive force that is perpendicular to the surface. You have to remember this. This come out perpendicularly, and hence it requires works to move molecules to the surface against this opposed force, and surface molecules have more energy than the interior ones. So higher force of attraction at surface. This is actually surface tension for different fluids and creates stretched membrane effect. So surface tension actually sigma as the force resulting from the molecular attraction at liquid surface. Surface tension varies with temperature, and this can be measured with this. Actually, surface tension F equals to surface tension sigma s, and L is the length over which the surface tension acts. So this is the capillary tube, and this is the water, and this is the mercury. So you remember that water in a capillary tube and very small tube filled with water. This make concave curve here, okay? But here convex curve, right? So this made due to the adhesive and cohesive force between the molecules of the water and mercury. So So rise and fall of liquids in a capillary tube is caused by surface tension. Okay, so capillary depends on the relative magnitudes of the cohesive of the liquid of walls of the containing vessels. When the adhesive force between liquid and solid are larger than the liquid's cohesive forces, the meniscus in a small diameter tube will tend to concave. That means this is the concave. This is called also meniscus. Okay, half circle. This half circle is called meniscus. So, and difference between adhesive and cohesive, a distinction is usually made between the an adhesive force which acts to hold two separate bodies together, and cohesive which acts to hold together the like or unlike atoms, ions, molecules of a single body. So capillary effect in surface tension we will calculate later. This is the length, sigma is the actual surface tension. So we'll calculate it in 9. Now, what is the actually fluid mechanics? It is the branch of science which deals with the behavior of fluids at rest as well as in motion. And fluid static, the study of fluid at rest, and fluid kinematics, the study of fluid in motion where pressure forces are not considered. And fluid dynamics, what the study of fluids in motion where pressure forces are considered. And this is the actually definition of density. Density or mass density of a liquid is defined as the ratio of the mass of fluid to its volume. So the mass per unit volume is called the density. And a specific weight density, what? Actually, a specific weight of a liquid of the ratio between to the weights of a liquid to its volume. So W equals to rho Z. Rho means what? Density. Now, specific volume is also measured by the volume of a fluid in per unit mass, 1 by rho. And a specific gravity also S equals to density of liquid in divided by density of water. Now we can define as the viscosity Chandrota. A viscosity is defined as the property of a fluid which offers resistance to the movement of one layer of fluid over another adjacent layer of a fluid. This is the actually velocity profile, and this is the u and this is the dy. This ratio is the curve this. And this is the shear stress is proportional to the rate of change of velocity with respect to y. So tau equals to this. And this is the Newton's law of viscosity. And this is the formula for measuring viscosity. And types of fluid: ideal fluid, real fluid, Newtonian fluid, non-Newtonian fluid. And this is the graph for every fluids. And we also effect of temperature on viscosity. Viscosity decreased with increase in temperature of liquid. Viscous forces, cohesive force, molecular momentum transfer. In liquid, the cohesive force dominates due to the closely packed molecules. So now the what is the actually surface tension? And this is the surface tension is defined as the tensile force acting on the surface of the liquid in contact with gas or on the surface between two immiscible liquid. Surface tension on liquid droplet P equals to, actually this is one kind of pressure, this 4 sigma by D. So a surface tension on a hollow bubble, this will be like this. So the surface tension is on a liquid will be this. This is the pressure, sigma is the surface tension, this is the diameter, and L is the length of the water set. So in capillary tube, capillary tube means very small tube, and we will calculate the surface tension on a capillary tube. Expression for the capillary lysis we will discuss in later. This is the weight of liquid, rho z pi d square H by 4. This is the surface tension for plain water or pure water. But remember that for pure water, theta equals to 0 degree and cos theta equals to 1. Expression for the capillary depression. This is the vacuum pressure. And different types of measurement. So this is the properties of liquid and gas. We have differentiated them in previous slide. So this is the dimensional unit. The dimension have the same for each term. and length L, time T, mass M, force ml per T. This is the dimension, and quantity velocity B, acceleration, and this is the measurement area, and volume will be B, discharge and pressure P, gravity Z. These are the actually properties of this. Is also, and surface tension will be given by sigma or capital T, and bulk modulus is the kinematic viscosity B, and dynamic viscosity mu, the specific weight and density rho. This is the symbols and dimensions and quantity we have to use in fluids properties. So in SI unit, that means in international system of units, we have to use as the Newton for the force. So rho equals to m by b, that means mass per unit volume is called the density, and density is measured by this formula. The specific weight also, a specific gravity, relative density is the ratio of a specific weight of fluid to that of water at standard temperature and atmospheric pressure. And a specific volume also can be defined as this, and viscosity is also can be defined with this. And we can use the in plot the graphically to find out the coefficient of viscosity. This is the unit of viscosity, Poisson, 0.1 Pascal. Vapor pressure, this is an example for solve. So what is surface tension? Actually, the surface tension, gamma, is the magnitude force of the force exerted parallel to the surface of a liquid divided by the length L of the line over which force acts. That means the force in per unit length is called surface tension. The SI units of surface tension is Newton per meter, and this is the actually definition for surface tension. So surface tension at the surface between liquid and gas or two immiscible liquids forces develop a forming an analogous skin or membrane at stretched over the fluid mass which can support weight. The skin is due to the membrane of a cohesive force. The interior of the fluid is in balance as molecules of the like fluid are attracting each other, while on the surface there is a net inward pulling force. So surface tension is the intensity of the molecular attraction per unit length along any line of the surface. So surface tension is a property of the liquid type, the temperature and the other fluid at the interference. So this is the membrane can be broken with surfactant which reduces the surface tension. Now this is the surface tension liquid drop. The pressure inside a drop of fluid can be calculated using a free body diagram, real fluid drops. This is the actually in microscope, and mathematical model. This is the force in per unit length can be reason, and a capital R is the radius of the droplet, and sigma is the surface tension. So del P is the pressure difference between the inside and outside pressure. So the force developed around the edge due to the surface tension along the line can be measured 2 pi r sigma. That means total surface force in the whole circumference. So twice pi r sigma. The force is balanced by the pressure difference, a little bit pressure del P can be applied to it. So In that case, pressure equals to del P pi r square per unit area. So surface tension for liquid drop can be written as this del P to sigma by R. Now, is the pressure inside bubble of water greater or less than that of droplet water? So surface tension in a capillary action, this is the actually concave, and this is the convex, and this is the adhesive greater than cohesion, and cohesion greater than adhesion. So this is for the water, and this is for the another liquid, mercury. Okay. So now we will discuss about the now surface energy of a surface tension. Surface energy and surface tension is discussed. This is the actually a liquid surface contacts spontaneously. Free energy is associated with its work. Take a rectangular frame PQRS with a horizontal wire AB. Dip it in a soap solution. A film is formed and across AB RQ. Okay, A B R Q. So this film actually due to the surface tension. To keep the wire in equilibrium and position, force has to be applied downwards. That means total force will be F, and F can be equal to first weight plus second weight. Where first weight is the weight of the wire and second weight is the extra weight to be used. Now, when the wire AB is pulled downwards through a distance del x for a little length del x, the area of the film is increased. The molecules in the bulk of the liquid move into the surface layers. They assume that the temperature remains constant. Work done equals to F multiply a small length. Force multiply uh, a little displacement is called work done. So increasing in areas taking place in both sides of the film. So there are two layers. This is why the total increased surface area will be twice Lx, length multiply breadth. Here L is the length of the wire. Work done per unit area will be this F by twice L. So thus work done per unit area gives the actually increase in potential energy per unit area of the film. This increase in length energy per unit area is called surface energy. So the force will be F capital T twice L. Here it is the if T is the capital T is the surface tension, then surface tension equals to force per unit length. This is numerically surface tension is equal to the surface energy. Suppose this is the quantity of heat absorbed per unit area from the atmosphere, then as S is the actual units of work, and S multiplied twice LF del X equals to this or S equals to T plus S. Here S is the surface energy and T is the surface tension, and S is the amount of heat absorbed by per unit area from the atmosphere. In that case, surface tension can be written as S minus S. Then S minus S is called mechanical part of the surface energy and is also called the free energy of the surface. Therefore, surface tension is equal to the mechanical part of the surface energy and also defined as the amount of work done in increasing surface. If the process is adiabatic, that means heat cannot be absorbed, then A is equals to 0. In that case, surface tension equals to surface energy. So the this is the and pressure difference across and spherical. Suppose, for example, a liquid drop of radius capital R breaks up into 64 small drops. Calculate the change in energy. Now, let the tension of the liquid will be capital T and radius of the bigger drop will be capital R. Surface area of the bigger drop will be 4 pi R square. This is the formula for sphere, গোলকের ক্ষেত্রফল. So volume of the bigger drop will be 4 by 3 pi R cube. Then let the radius of each small drop will be smaller. So capital volume of capital drop equals to 64 into a small volume of a small drop. In that case, small r equals to capital R by 4. Surface area of each small drop will be this, and 4 pi r small r equals to capital R by 4. This is so on. So surface area of 64 small drops will be this. Increase in area, just minus 12 pi r square. Change in energy, what will be? Surface tension multiply increase in area. This is the actually total 12 pi t r square. Similarly, we can calculate another example. Calculate the amount of energy needed to break a drop of petrol of volume 10 to the minus 6 meter cube into 1000 millions drops equal size. Surface tension of petrol will be this. We must know the volume of the petrol drop 4 by 3 pi capital R cube and 10 to the minus 6. This is given. So R cube equals to this, and R can be calculated. Also 4 by 3 pi R cube equals to this one, and in that case small this equals to actually 10 to the 9 into a small drop of petrol. So small radius of a small drop will be this. Increase in surface area, this minus this, and I increase in surface area will be just putting the capital value of a small r and capital R. So we get calculated a capital I equals to this, and so surface tension will be this, and required energy surface tension multiply A. So this is the joule. Similarly, we can calculate the work done in spraying a spherical drop of mercury of radius this into a million drops. So capital R equals to given radius this. So 4 by 3 pi r cube equals to this small radius. Million means what? 10 to the power 6. 10 to the power 6. This is why mercury drop, volume of mercury drop equals to 10 to the power 6 into small 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 drops of mercury. So radius of a small drop will be this 10 to the minus 5. Increase in surface area and work done. Very easy. This is also easy example for you. Similar example. And this is also similar example. The amount of energy will be the liberated 10,000 droplet, 1,000 droplet of water, each 10 to the minus 8 meter in diameter. So small r equals to this divided by 2. Okay. This is the diameter, and radius will be half of this. So 0.5 into this. And volume of the droplets equals to bigger droplets equals to 1000 into volume of smaller drops. So capital R equals to this. So decreased in area, right? And energy liberated this. Similarly, spherical soap bubbles of radius 1 centimeter in blown, and we can calculate this example. And 8.7 also can be calculated. Very easy example. And this example, similar example. This is also excess of pressure. Calculate this also, and pressure, excess pressure 40 divided by R, because there is excess pressure between the inside and outside of a soap bubble. Now excess of pressure inside a spherical liquid drop or an air bubble in a liquid. Imagine a drop of this is a drop of a liquid or a soap bubble to be divided into two equal hemisphere. This is, that means this is equally, this full drop can be divided into two hemisphere, an orthogulok, horizontal plane ABCD. Let the pressure inside and outside P and P2. In this case, surface area, the face area ABCD will pi r square. Okay, area of circle. And thrust due to, that means pressure P2 equals to P2, and per unit area will be P2. This is why total thrust will be upper surface and lower surface will be this. The thrust into the, due to the surface tension, capital T into S pi r. This is the circumference. The tension, surface tension acts around the circumference of the drops, which is this. So for equilibrium, we can get this total thrust equals to P1 pi r square. Similarly, P1 minus pi 2 equals to this. Let the excess of pressure by P equals to P1 minus P2 and P equals to twice T by R. Okay. The unit excess pressure in CGS system dynes per square meter. So centimeter. This is the expression excess pressure inside the soap bubble. Similarly, this is the pressure 4T by small r. Excess pressure is inversely proportional to the radius of the drop of the bubble. Now, the difference of pressure across a curved surface. This is actually a surface AC, and the another dual surface A dash, D dash, C dash. So AD is the original curved, and A dash D dash is the new changed. So this R1 is the radius of the original curve, and the R2 is the radius of the newly shaped. So AB equals to original length x and BC is the y. So BB dash equals to smaller change in del z, and A dash B dash equals to x plus del x, and B dash C dash equals to y plus del y. Now if we consider a curved membrane, the element of the membrane is in equilibrium only if the excess of pressure acts on the concave side. This excess of pressure balances the effects due to the surface tension. The magnitudes of the excess of pressure can be calculated as follows. Suppose ABCD be the element of the curved surface having principal radius R1 and R2. Consider that the element has one surface only. Suppose the excess of pressure on the concave side is P. This is the pressure P. So surface area ABCD equals to XY, and let the surface area xy be given as small displacement del z. So it takes the position A dash B dash C dash D dash parallel to itself. Then the surface area is increased. The increased surface area will be what? Sigma xy. So sigma xy equals to what will be? X into sigma y plus y into sigma x. Let the surface tension be capital T. Work done will be T equals T multiply. This is the surface area. Okay. Also the work done by pressure will be Px U del Z. So from equation 1 and 2, equilibrium. So triangle ABU and A dash B dash O are the similar. So the ratio of sides will be equal. Okay. So A dash B dash divided by OB dash equals to B by OB from figure, and A dash B dash minus AB divided by OB dash minus OB. So this ratio, putting the just values, del x equals to x by r1 del z. Similarly, it can be proved that del y equals to y by r2 del z. This is the first of our first curve, and this is for the second curve. Now substituting the values of del x and del y in equation 3. So just putting here, we get the equation. This expression is also true for the liquid drop or an air bubble in a liquid. In a special case, the liquid drop or an air bubble, if the radius are same, then we get the pressure twice T divided by capital R. In the case of soap bubble, there are two surfaces. This is why R1, R2 equals to R. The same. So P equals to surface tension will be 2 times, because there will be two surface in the soap bubble. This is why 1 by R plus 1 by R, 4T by R. If the surface is in cylindrical, so in cylinder we must know the radius are equal. So the and the second radius will be infinity. This is why 1 by r plus 1 by infinity equals to 0. This is why t by r. For a hollow cylindrical film, this twice to r. Now angle of contact. The angle of contact is theta, hence the angle of contact is defined as the angle made by the tangent at the point of contact of the liquid surface with tangent plane to the solid surface inside the liquid. This is the angle of contact definition. Remember that the angle of contact of the cases of water is acute, that means less than 90 degree, Shukkokun. And in the case of mercury, the angle of contact is obtuse. Obtuse means what? Stulokon, that means greater than 90 degree. And so this is the for water. This for water angle of contact will be the less than 90 degree, and for mercury bigger than 90 degree. So this is the explanation inside the water, and this is the inside the mercury. Now determination of angle of contact. Angle of contact for mercury in glass. The angle of contact, this is the angle of contact for mercury. This is the greater than 90 degree, you must know. And I take an open spherical glass flask. The lower end of the flask is connected to the reservoir R through a rubber tube. The flask is graduated vertically on its outer surface to reach the level of the mercury above the point O. Here O is the center of the flask. The position of the reservoir R containing the mercury can be adjusted as desired. So if the adjust the reservoir R such that the level of the mercury in the flask appears horizontal. So angle of BAD equals to theta. It is equal to the angle of contact, that equals to 90 degree plus pi. So sin pi equals to, you must know from the triangle, perpendicular divided by hypotenuse. A is divided by R. OB equals to A is OA equals to R in the figure. Okay, you must know. This is the length and this is the hypotenuse. So from sin pi here measuring A and R pi, it can be calculated. Thus the angle of contact theta for mercury can be determined. Now angle of contact for water, you must know the angle of contact will be less than 90 degree. So for water, theta equals to 90 degree minus pi. In that case, here sin phi equals to A is divided by R. This is the alternative method. Now, another example. A large drop bubble of radius contains inside it a small soap bubble of radius b. The smaller bubble burst isothermally with no leakage of air from the system as a whole, and a new bubble of radius capital R is formed. Show that this relation. Now let us consider atmospheric pressure P, surface tension T. Let the pressure inside the three bubbles P, P1, P2, P3. You must know first pressure capital P plus 4T by A, and P2 will be P1 plus 4T divided by B, and this, and for the pressure 3 will be 4T divided by R. For the isothermal process, you must know Boyle's law satisfied. That means pressure volume ratio will be equal. So P2 B2 equals to P1 B1 plus P3 B3 equals to P1 B1 plus P2 B2. Just putting the relations. Substituting the values of P1, P2, P3, we get the relations. Now, two subbubbles of radius A and B coalesce to form a single bubble of radius R. If the external pressure is P, prove that the surface tension of the solution form from which the bubbles are formed is given by this. This is the capital T is the surface tension. We have to remember that temperature will be the constant. Let PR, PA and PB be the internal pressure of the bubbles of radii RAB, okay, at constant temperature. You must know from the Boyle's law, PB, PR, BR equals to PA, BA plus PB, BB. Just putting the volume 4 by 3 pi r cube, volume of earth bubble, and 4 by 3 4 by 3 pi r cube, 4 by 3 pi b cube. This is the bubble of radius b and bubble of radius a and bubble of radius small r. So cancelling from both sides 4 by 3 pi, we get this. Now also PR minus P equals to this 4T by R, PA minus P equals to 4T by this, and PV minus P would be this. So substituting these values in equation 1, we get the relation easily. In an experiment for determining the surface tension of water by capillary rise, a capillary tube of diameter 1 millimeter is used. The height of water will be now capital T is what? So rise will be 0.03 meter, D equal to 1000 kilogram per meter. So Z equals to 9.8 and you must know surface this pressure twice T by R equals to S dz. That means capital T is dz by 2. Just calculation. Now similarly, this is also very easy example for you. This is also similar example. This is also subbubble problem and a subbubble problem. Now, what is the capillary? Capillarity. When a capillary tube of a fine bore is dipped in water, water rises in the tube. খুবই ছোট একটা টিউব যেটার রেডিয়াস খুবই ছোট, এখানে কিন্তু পানি ঢুকলে কিন্তু সহজে বের করা যায় না, পানিতে ডুবালেই কিন্তু পানি ঢুকে বসে থাকে. Water rises in the tube. A tube with a fine bore is called a capillary tube. Now, on the other hand, if the tube is dipped in mercury, there is depression of mercury level in the tube. This is actually for water and this is for mercury. That means concave, this is the convex. Angle will be what? Less than 90 degree here for water, and angle will be angle of contact will be greater than 90 degree. That means obtuse angle. Now expression for surface tension T, will try to find out the surface tension. You must know this is the actually capillary tube and this is the rise of water, and the angle of contact will be less than 90 degree, and this is the surface tension T. But this surface tension actually has two components. One is along the base T cos theta, and along the perpendicular side T capital T sin theta. Similarly, for the upper portion at point B also, theta is the actually angle of contact, and capital T is the tension, surface tension, and this surface tension has two components, one along the base T cos theta and along the perpendicular capital T sin theta. But remember that capital T sin theta and this capital T sin theta will be the balanced and can be negligible. But the only active tension, active surface tension or active force will be along what? Capital T cos theta. For this action, the rise of water happening. Okay, the rise of water happening for this. So only active surface tension will be, active force will be what? Capital T cos theta. So this capital T cos theta and this capital T cos theta, how many? 2x T cos theta. So force per unit length equals to T cos theta, and circumference will be twice pi r. So total upward T cos theta twice pi r. This upward force balance the weight of the liquid column in capillary tube. Height of the liquid column will be H. Volume of the liquid in the meniscus. This is the actually meniscus, this one. Okay, this is the half of sphere. So volume of the liquid in the meniscus will be pi r square. This is the multiply r. This is the radius, and 2 by 3 pi r cube. This because this is the half sphere. That means half into 4 by 3 pi r cube. This is why 2. Okay, 2 by 3 pi r cube. So this minus equals to 4 r cube by 3. Now volume of liquid in the column will be what? this volume of the pi r square is, this pi r square is means this this volume. Okay, this volume will be pi r square is, because s is the height and r is the radius. So this cylinder volume will be pi r square is, and another one is half sphere. So total volume of the liquid will be pi r square is, and the volume of the meniscus. Okay, so okay, taking common pi r square is plus r by 3. Density of the liquid will be rho. So weight of the liquid equals to pi r square into this rho z. Now equating equation 1 and 2, you must know twice pi r t cos theta equals to pi r square this, and capital T equals to r s plus r by 3 rho z by 2 cos theta. But remember that when the angle of contact is 0, that means angle of contact cos theta equals to 0 for pure water, capital T equals to will be this. Now determining the surface tension for water. Suppose for a particular tube, the radius is r, the height of the water is h, the density of water is rho, then the surface tension we have calculated in room temperature, capital T equals to r is plus r by 3 rho z divided by twice cos theta. But taking for pure water, theta equals to 0, angle of contact, and cos theta equals to what will be cos 0 degree equals to 1. So in that case, capital T is this. So here the surface tension of water can be determined, just putting the values of rho, rho density small z, acceleration due to gravity, r is the radius. Now determination of surface tension of a liquid by Giger's method. Giger's method is based on the principle that excess of pressure inside air bubbles in a liquid is capital T by twice T by r. So capital T is the surface tension of the liquid and r is the radius of the bubble. So in that case, this is the air bubble produced here, and excess of pressure inside the bubble will be twice T by R. Pressure of the liquid column H rho Z. This is the formula for pressure, H rho Z. Atmospheric pressure P, excess of pressure twice T by R. This. So pressure inside a bubble, total pressure P H rho 1 Z twice T by R. Rho 1 is the density of the liquid. The difference in level in the two limbs of the manometer when the bubble just burst equals to is density of the liquid will be manometer will be rho 2, and pressure of the air manometer will be P plus is rho 2 Z. Equating equation 1 and 2, we get actually capital T equals to this one. Actually, this is the radius of the capillary tube is measured with the help of traveling microscope. As all the other values are known, the surface tension capital T of the liquid can be determined. This is the method for and this is also called Giger's method, Giger's experiment of a capillary tube. So this is the example relating to this expression twice T by R equals to H root 2 Z minus H1 rho 1 Z. So the capillary tube of a internal diameter is this, dips and a meter inside water contained in a beaker. Okay, beaker means actually look like a glass. The difference in a level of water manometer when the bubble is released is 0.09 meter. Calculate the surface tension of water. So just putting all the values, we get the result. Actually, we have discussed fluid mechanics in a short view. Fluid mechanics actually, fluid means you must know gas and liquid, and mechanics means actually statics and dynamics. So in that case, fluid mechanics, there are two types of fluid. One is gas types and other is liquids. So mechanics also two types, statics and dynamics. Actually in a statics, force acting, but the total force will be 0. And in dynamics, force acting, but force will be non-negative. That means positive. Then force will be greater than 0. That means flows of occurring. And you must know gas means air, helium, argon, neutron, etc. And liquids means water, oil, alcohol, etc. But in statics means stability, pressure, buoyancy acting, and in dynamics actually um, flows occurring. And flow means it laminar or turbulent, compressible, incompressible, steady or unsteady fluids. So there are different kinds of fluid dynamics and fluid statics also. And this actually liquids also compressible density, viscosity, surface tension, vapor pressure, etc. And so statics also this reaction and dynamics. This is the overview of fluid mechanics. Now, effects of temperature on surface tension. Actually, the surface tension of liquid generally decreases with the increase of temperature and becomes zero at critical temperature when meniscus between the liquid and the vapor disappears. The decrease in surface tension with increase of temperature is due to the fact that the increase of temperature, the kinetic energy of the molecules increases and hence thermomolecular attraction decreases. So according to Oudbas 1886, he calculated an equation as gamma m by d whole to the power 2 by 3 equals to k Tc minus T, where m is the molecular mass of the liquid and d is the density of the liquid at temperature T degrees centigrade, and Tc is the critical temperature of the liquid, where the temperature at which surface tension is equals to 0, where gamma is the surface tension of the liquid at temperature T degrees centigrade. But at critical temperature, gamma equals to 0 and K is a constant. So M by D is the molecular volume of the liquid. If the volume is taken be spherical, then M by D to the power 2 by 3 is molecular surface of the liquid if they are spherical. And gamma is the surface energy of the liquid. Therefore, this is the molecular energy of the liquid. And further, Ramsay and Shields in 1893 found that, and this is zero at critical temperature. So, but at T equals to critical temperature minus 6, that is temperature at 6 degrees centigrade less than the critical temperature, hence then the modified equation will be like this. So, and will be negative at critical temperature. To overcome this difficulty, Katayama suggested a more correction relation like this: gamma, then is surface tension into m by d minus a small d. Small d is the actually density of the vapor at temperature T to the power 2 by 3 K Tc minus T, where d is the temperature, small d is the temperature of vapor at temperature T. In this equation, gamma equals to 0. Now, you must know about the viscosity. Viscosity of a liquid is a measure of its fractional resistance. So this is the molecular layers and moving plane and velocity profile, and here B equals to 0 and here B acting in a moving plane. So stationary plane, flow of liquid on a glass surface area equals to capital A, and if you move dB, so B plus dB, and the distance change will be dx. So in that case, we can calculate F is proportional to the surface area into dB dx. So F equals to eta A dB dx, and eta equals to this one. So eta is the actually proportionality constant. It is known as the coefficient of viscosity or simply viscosity of liquid. And eta has a specific value for a given liquid at the same temperature. It may be defined from equation 2, this as the force of resistance per unit area, which will maintain unit velocity difference between the reciprocal of viscosity is called the fluidicity and is denoted by pi. Pi equals to 1 by eta. Units of viscosity will be this. Eta can be calculated from the equation 2. F by A dx dB, force divided by area, distance by velocity. It equals to, and force equals to mass length time to the power -2. So we get this in CGS. And measures of This is the measures of viscosity with a Ostwald viscometer. Now, effects of temperature on viscosity. The viscosity of a liquid generally decreases with the rise in temperature. Actually, look like surface tension. This decrease is appreciable, being about 2% per degree rise of temperature in many cases. This has been explained in terms of Hall theory, and this is the actually Hall theory for explaining the effect of temperature on viscosity. This is the empty holes and this is the fluid. So we can calculate this and plot the eta and effect of pressure. On increasing pressure, viscosity of liquid increases. This is due to the fact that they decrease in the number of holes as the pressure increases. Therefore, it becomes more difficult for liquid molecules to move around, and thus it becomes more difficult for them to flow. So this is the effect of pressure, effect on temperature and pressure of surface tension and viscosity. This is an open problem for you. A soap bubble and a liquid drop. This will be the a student using a circular loop of air and a pan of soapy water um, produces a soap bubbles whose radius is 1.0 millimeter. The surface tension of the soapy water is this, and find the pressure difference between the inside and outside droplet. So this is the open problem. If the bubble and drop had the same radius, we would expect that the pressure difference between the inside and outside of the bubble to be the twice as larger as the that for the drop. The reason is that bubble has two surfaces. This is why pressure increases two times, and whereas the drop has only one. So the bubble would have the twice the force due to the surface tension, so that the pressure inside the bubble would have to be twice as larger. Now solution, we'll get the solution. This is for the pressure difference and pressure difference. This is the open problem for you. If you this is open problem for you, you'll do it, you'll practice it at home. So thanks to everybody. Actually, we have discussed here surface tension and these topics. Thanks to everybody.